having a good day. Not doing too bad here. Keeping busy at least. Here we have a Burgess inverter drive, and it is model number ACM-2 11.0 kW. And it was coming up with an error 9 alarm. Error 9 in the LCD display. Now that's output stage error. When I checked L1, L2, and L3 UV and W to bus plus and bus ground, there was no short circuit. So what was causing the error 9? What I ended up doing was replacing this IGBT. It's not shorted, but we'll look at it with a DMM here in a little bit, and you'll see that there's just one output that's a little bit different from all of the other ones. Cut this IGBT off the power board, installed the new IGBT, and it's working. It is working. Look at that. Let's run it again. There's 24 hertz displayed on the LCD. It's running that spindle motor very nicely. Let's take a look at this IGBT with our meter. Let's see if we can see the difference. It'll amaze you. And then we'll take this IGBT and we'll fire it with a light bulb load on one good IGBT and on the bad IGBT and see what happens. Let me go get my meter. Now what you're going to see is very peculiar. Now I've labeled the IGBT. Let me turn it around so you can see those letters upright. So these two terminals on each side are bus plus. These two terminals on each side are bus minus. Here's the U terminal, the V terminal, and the W terminal. Now what we're going to do is we're going to take our black lead and put it on bus plus in our U, V, and W with our red lead. Then we're going to take our red lead, put it on bus minus, and the black lead on U, V, and W. Did I get that right? Well, let's try. And what you're going to find is that everything looks normal as far as diode drops go. But then we're going to dynamically test two IGBTs of the 6, one good and one the bad. And you'll see the oddity that doing a diode check does not always tell you that you have a bad IGBT. So black lead on plus, Get on her. And we have 0.391 from bus plus to U. Here's V, 0.390. Here's W, 0.391. Now, if it were me, I'd say that was good. Now we're going to put our red lead on bus ground and do the same thing with the black lead. U, get on her, 0.391. V, 0.391. W, 0.391. Now I'd say that was a good IGBT. Let's go dynamically test it with a light bulb load. Here is our IGBT that we're going to test. This is a gate firing circuit that I have built up on this breadboard. I'll put a drawing up of it at the end of the video, and you can make you one. I believe I did make a video of this at one time. Maybe I'll reference that this video back to that one, and you can take a look at that. But still, I'll put the drawing up. This variac and DC bus power supply, it's a bridge rectifier, bus capacitors, are going to make the high voltage for the IGBT, and it's connected to plus bus and bus ground terminals. Here is our load that we're going to use a light bulb load, and it is connected right now to the W terminal back to bus ground. Here are the gate and emitter for the high side W output, the IGBT of the high side W. The gate and emitter are at the final stage of our gate firing board right here. This power supply is supplying 5 volts to the 555 timer and the input side of the optocoupler. This right here is set to 15 volts, and that is our gate firing voltage. Let's turn everybody on and we'll see what happens. Plugging in the variac, and I got it set to 0 volts right now. Everybody's powered up. This LED indicates that the output of the 555 is oscillating. And the scope is set to 50 volts per division. Here, you can see that the light bulb is turned on. The output of the gate firing board is turning on and off the gate, which in turn is switching on and off that IGBT inside this 6 IGBT package. You can see this is our load right here. At this point, the light bulb's turned on and then off and on and off and on and off. Now, when we turn the system down, when we turn it off to move to the second IGBT, this is the good IGBT, we're going to move to the bad IGBT, which is the U high side IGBT. When we turn this off, what we want to do is we'll turn the variac off. Our signal has gone down. Unplug the variac while it's still firing to ensure that the high voltage has been removed from the IGBT before we disconnect anything. Now let's turn the gate firing board off. What I do is I disconnect the W, then I move the gate emitter and connect them to the next IGBT. You want the gates hooked up before you put the high voltage on. Look at that. light bulb's turned on, but there's no gate firing. That IGBT is not turning on and off like it should. Let's get you close to the oscilloscope. We'll look at the good one first, the good IGBT, and then we'll look at the bad IGBT waveforms. Let's move back to the good one. Disconnecting the U high side IGBT. Hooking the gate emitter to the W high side IGBT. Let's look at that oscilloscope. Alright, this is 50 volts per division. Looking at the light bulb load, I'm increasing the variac. And right there's a peak of 50 volts. We're going to stop right there. The light bulb is turned on, and you can see that that IGBT is turning on and off. That is amazing. So that's a good IGBT. Let's go look at the bad one. Now we were looking at the high side W IGBT. We've moved our connections over to the high side U IGBT, and we're going to test that. We have the system powered up. I'm increasing the variac. Look at that. Look at that. It doesn't turn on and off. It does not turn on and off, and that light bulb is on. That light bulb's turned on. So there's the peculiarity. It tested good with my meter. My meter said that that was a good IGBT as far as no short circuits are concerned. But when we dynamically test that IGBT, we see that the high side U IGBT is bad. It does not switch on and off. And that right there was causing that error 9 in that Burgess inverter drive. Isn't that fascinating? So in the future, if your Burgess drive says error number 9 and your meter says that that IGBT is not shorted, it's probably a good idea to change it anyways. Okay. All right, everyone. Wasn't that fascinating? Let's power everybody down and we'll head to the hooch. Thank you for stopping by. Enjoy the time with your families. And we'll see you next time. Here are the pinouts of the IGBT that failed. Error number 9 in that Burgess inverter drive. Part number BSM75GD120DN2. This IGBT right here, W high side, we have a high side IGBT and a low side IGBT. When I mention high side and low side, the high side IGBTs are tied to bus plus. The low side IGBTs are tied to bus ground. And in between we have U, V, and W. So our U high side IGBT is the IGBT that failed. 9 and 10 are the gate and emitter of that U high side IGBT. Terminal 15 right here is the output of this high side and low side IGBT. The IGBT that we tested good was the W high side IGBT. We needed a comparison from W high side good and U high side bad. Now on the W side, 1 and 2 were the gate emitters of that IGBT. Terminals 13 and 21 were bus plus. Terminals 14 and 20 were bus ground. Now, when we tested IGBT with our digital multimeter, the Fluke digital multimeter, what we were doing, we were looking for short circuits. So I took my black lead and connected it to bus plus, and I took my red lead and went to terminal 19, and we had a diode drop, I think, of 0.391, terminal 17, and terminal 15. We had good diode drops there. What we're actually measuring when we do that, we're looking for short circuits or something that is different from all of the others. So for instance, if I put my black lead up here and my red lead on terminal 19, the output of this IGBT right here, and I saw a 0.391 voltage drop, and then I went over here and did the same thing on terminal 17, which would be V, and I saw like 0.140 as an example. Well, that's totally different from these two out here, and that one would be the bad one. Does that make sense? Then we went down here and put our red lead on bus ground, and we went from W, V, and U, and we saw the same diode drops, 0.391 if I'm not mistaken. So the IGBT, according to my meter, was good, but when we actually drove into this IGBT with a light bulb load, this one worked, but this one was on all the time. I'd like to tear into that IGBT someday and try and figure out why, even though we were gating that IGBT on and off, it never switched at the output from collector to emitter. Amazing, some of these things you see. So, what actually are you seeing when we diode drop from, say, plus bus to the W output, or bus ground to the W output? There's a freewheeling spike suppression diode built into these IGBTs. That's what we see right here. These 6 diodes. Now, if we had a short circuit from, say, bus plus to 19, we would see the short circuit from collector to emitter, cathode to anode, through this circuit right here. That's how most IGBTs fail. You'll have a short circuit through collector to emitter. When we do our diode drop, and this is inherent in every IGBT, you will have this diode right here. And what we're measuring, if there's no short circuit right here, we're measuring the cathode, we put our black lead up here on the cathode and our red lead down here on the W output. We're measuring the spike suppression diode, the freewheeling diode that's built into that IGBT. So we have black lead on cathode, red lead on anode. Hello, here we are again. Now this is the high side W. Here's the low side W. Here's the high side U and the low side U. 13 and 21 are the plus bus terminals. 14 and 20 are the bus ground terminals. That's why we call this the high side and this the low side. In between this totem pole is the output to the motor winding, the W motor winding, and in between here is the output to the U motor winding. 1 and 2 are the gates of the high side W. 3 and 4, these are terminals on that IGBT power package. 3 and 4 are the gate and emitter of the low side. Here, 9 and 10 are the gate and emitter of the high side, U IGBT, and 11 and 12 are the gate and emitter of the low side, U IGBT. Now we tested the high side W IGBT good as a comparison to the high side U IGBT. This one failed and this one was working. Now here, let's put, I hope I can draw this right. We had this is turning out horribly. I should have done this off camera. But here's our 100 watt, 100 volt light bulb right here going to bus ground. These terminals down here. And when we applied a gate voltage, a square wave gate voltage of 0 to 15 volts, we were able to see that this IGBT from bus plus through the collector emitter was turning on and off. We looked at this point right here with our oscilloscope, reference to bus ground. Now let me see if I can do this a little bit better over here. We'll draw another light bulb going to bus ground. Shoo. Then we move this light bulb over here to this terminal, 15. 19 being the W output to the windings, and 15 being the U output to the windings. Now what we found when we applied that 0 to 15 volt square wave, pin 9 reference to 10, this IGBT was on all the time. It never gated on and off at the output. And that is why we got the error number 9 on that Burgess inverter drive. Now let's go look at the circuitry that we used to gate on and off this IGBT and this IGBT. But before we do that, let me back up a little bit. What if you want to check the low side? What if you want to check the low side? Well, what we would do, we would tie this to bus ground of our bridge rectifier, variac, and bus capacitors. And we would bring pin 19 up through a light bulb to this connector right here, bus plus. And then we would gate on and off. We would turn on and off pin 3 reference to pin 4. And so that this IGBT would be turning on and off. And then we would have our light bulb turned on and off right here to bus ground. It's amazing little circuit that you can put together right there. Well, let's grab that circuit that we used to turn on and off the gates of these two IGBTs right here. And these two if you wanted to. This is the IGBT that we're driving into with our test circuit. It is part number BSM75GD120DN2. Here is our light bulb load connected to W. Now the W circuitry was good in that IGBT power module. The U circuitry was bad, and we saw that in the video. So we have a light bulb here connected to the W output going to bus ground. Everything on this side of the optocoupler, CNY17-2, is referenced to bus ground. The bus ground that we created with the variac, the bridge rectifier, and the bus capacitors. Everything on this side of the optocoupler is referenced to plus 5 volts DC and ground of an external power supply. I have an NE555N which is set up to run in a stable mode of operation. That means that it will always output a square wave when we apply 5 volts and ground to this circuit right here. As long as it's out of reset, and of course down here our reset bar is pulled up to 5 volts DC, so it's not in reset. The output drives into this green LED just to tell us that we have oscillation on the output pin 3 of the NE555, and that it's just an indicator saying that, hey, we've got up and we're going. It's always nice to have these little things right here to help you in kind of setting the system up and making sure it's going. So the output here, in addition to driving into this current limiting resistor and green LED, it goes over here through a 560 ohm current limiting resistor. We have to current limit these devices right here, otherwise we'll burn them up. So we have a 560 ohm resistor going to pin 1 that's routing our square wave of 5 volts peak into the anode of the input side of the optocoupler, CNY17-2. The cathode side is connected to that 5 volts DC external power supply. So as we have a frequency here that's turning on and off this LED inside that optocoupler, When the LED is on, it emits photons into the base of this phototransistor, causing it to conduct. And applying plus 15 volts DC through the collector emitter into the base emitter of this tip 121 through this 20k ohm resistor. When the LED is turned off, this transistor inside the optocoupler is no longer conducting, and the base of the tip 121 NPN transistor is pulled to ground through this 10 kilo ohm resistor, ensuring that it's turned off. So when it's on, pin 1, gate W, is at bus ground. We have collector to emitter turned on, and so that we have close to 0 volts across collector emitter. So we're at 0 volts right here. When this transistor is turned off, the gate W input is pulled up to 15 volts DC through this 1 kilo ohm 1/2 watt resistor, in effect applying that plus 15 volts here to the gate. So the gate is going to be on or off, on or off, on or off, and that's what we saw out here. On the W output, the high side W IGBT turning on and off, on and off, on and off, on and off. Now there's one thing I have to say about this circuit right here. I would not use this circuit in a drive to fire the high side and low side. The reason being is because, well, let me back up a little bit. We're only firing one IGBT. We're not firing both the high side and the low side. But in a drive, they fire the high side and low side. You don't want to fire the high side and the low side at the same time. So what they do in a drive is they will have circuitry that will, in our instance, will apply the plus 15 volts DC to the gate, and when it's turned off, when they don't want it turned on, they will pull that gate to a negative voltage. And we're not doing that here. We're just going from bus ground to plus 15 volts DC. Plus 15 volts DC to bus ground. So don't use this circuit to fire a totem pole circuitry in your IGBT, the high side and low side. Don't do that. This is only meant to turn that one on and off. Now, say for instance, what I'm trying to say is like, say this one's turned on and the low side is turned off. But when we want to turn the low side on, we absolutely must ensure that the high side is turned off. So we drive that gate negative to a negative voltage, and that ensures that no electrons in that gate are able to turn that gate on, because we've switched from positive to negative. Same with the low side. If you wanted to ensure that the low side is off, we turn while we're turning on the high side, you pull the electrons out of the gate with a negative voltage. Does that make sense? That's confusing, but that's how they do it. So this is only meant to fire one IGBT in that 6 IGBT package, just one.